Wrap this chapter up with geometric probability. You did probability in Algebra 1, so a lot of the terminology is going to sound familiar. The only difference is going to be we're going to put a little bit of a geometric twist to it. So some of it's going to be repetitive, and some of it you'll see when we get into the area of different figures how it pertains to geometry. So a couple of quick definitions. When you're dealing with probability, your sample space is going to be your denominator, as you can see here, and it's the set of all possible outcomes when you do an experiment. The outcome that you're trying to make happen, or the probability that you're trying to find for a certain outcome, is going to be called an event. So when you're trying to find the probability of something happening, it's going to be the number of outcomes in the event that you want to make happen. For example, landing on the number 1 when you have a 6-sided cube. So your number of possible outcomes is your sample space on the denominator, and the chance of landing on a 1 when you're rolling a cube is going to be your numerator. Geometric probability is going to be the probability of an event based on a ratio of geometric measures such as length or area. So the first thing that we'll look at, and this is going to make a little more sense when we start looking at some examples in a second, are examining lengths on a line. Okay, so your sample space, when you're looking at line AD, your sample space would be all the points on AD that you have. And then if you want to find the probability of landing on BC, then you're going to have the probability of BC over AD. The probability of landing on BC versus all the possible points. When you're looking at angle measure, your sample space is going to be the whole area of the circle. And if you want to find the probability of landing in this sector here, then it's going to be the measure of this sector over all possible options, so 360 degrees. And then for your area, if you want to figure out the probability of landing in this triangle, it's going to be the probability of the area of the triangle over the area of the whole rectangle. So as we go through some examples, this will make a little more sense. I guess this is landing on the circle, guys, not the area. This is going to be actual area measure. All right, so let's see what we have going on. So a point is chosen randomly on AD. And these are going to be your lengths here of your different segments. We want to find the probability of each event. So we want to find the probability that if a point is chosen randomly, it's actually on AC. Okay? So this is going to be the probability of landing on AC. Hopefully this notation looks familiar from last year. So we have the outcomes of landing on AC over the total outcomes of landing on AD. Okay, so I always start with my sample space. My sample space is going to be 4 plus 3 plus 5. So I have 12. And then the length of AC is going to be 4 plus 3, so 7. So the probability of landing on AC is going to be 7 over 12. For these guys, I don't care if you do it as a decimal, a simplified fraction, or a percent. Either one is perfectly fine with me. So if you guys look at this one, we want to find the probability of the point being not on AB, which is going to leave it landing on BC or CD or BD. Okay, so the sample space is still the same, it's still 12. And then if it's not on AB, then it's going to be either in BC or CD, so 3 plus 5. Okay, so you get 8 out of 12. Always simplify. And your probability for that event is going to be 2 over 3. Another way that you guys can do this, and that's what it says here, you're going to see me alternate it a little bit, is you can also find the probability of landing on AB, which would be 4 over 12. And then you can subtract that from 1. So 1 minus 4 over 12 is going to give you the probability of not landing on that, which again is going to be 8 over 12. So sometimes it might be easier to add what's left behind. Sometimes it may be easier to subtract. Whatever method you prefer, I'm fine with. So when you guys have OR, you maybe remember this from Algebra 1, you're adding. You see and you're multiplying, but we won't get into that in this class. Just some basic probabilities here. So we want to find the probability that the point is on AB or CD. Okay, so again, our sample space is going to be 12 for both. And remember, when you see or, you add. So the probability of landing on AB is 4 out of 12, and the probability of landing on CD is 5 out of 12. Or you guys can just stick it together, however you want to do it, and you get 9 over 12, which of course simplifies to 3 over 4, or 75%. So you guys will see some problems like this, really nothing crazy, just playing around with your different lengths of your segments. So now we'll look at our pointer here. Use the spinner to find the probability of each event. So this is what I was saying before when it talks about the degrees. We're looking actually at the arc length, not the area of the sector. We'll deal with the area in a few minutes. So we want to find the probability of the spinner landing on each event here. Okay, so we know that our sample space is going to be 360 degrees. And each of these is given a different degree. So the probability of the pointer landing on red is 80 degrees out of that 360 degrees. So simplify that and you get 2 out of 9. The probability of the pointer landing on purple or blue. So again, we're starting at 60 degrees. And purple or blue, we're going to add those together. And you get 135, which simplifies to 3 over 8. Okay, the probability of the pointer not landing on yellow. So I'll work this one out subtracting. So the probability of landing on yellow is going to be 100 degrees over 360 degrees, which is going to simplify to, let's see, 10 over 36, which is going to be 5 over 18. All right, so then 1 minus that is going to give me 13 over 18. Or, if you guys want to do it a little bit differently, if you don't like that method, then you can just add everything else up that's not in yellow, and you would end up getting 260 degrees out of 360, which is again going to simplify to 13 out of 18. Okay, so you'll get the answer, whichever one is going to work for you. Sometimes you have no choice but to use this method, which you guys will see in your homework. Alright guys, this is going to be the last thing we'll talk about is our area. So, find the probability that a point chosen randomly inside the rectangle is in each given shape, round to the nearest hundredth. Okay, so our sample space is going to be the area of the total rectangle. Alright, so if I take a pen and I drop this right on a field, a football field, and from a bird's eye perspective, what's the probability that it lands in the circle here? Okay, so the area for my whole football field is going to be 900. However, what's the area for the circle? Pi r squared. It says around to the nearest hundredth, so I'm just going to go ahead and crunch those numbers in my calculator. And you're going to get 0.13 or 13%. Alrighty, the trapezoid, same thing. My sample space is going to be the same sample space. It's going to be 900. Okay, and then remember for your trapezoid, 1/2 base 1 plus base 2, 12 plus 13, times your height, which in this case is 10. So they gave us everything. We didn't have to work too hard for this, which is good. You might have some where you have to take a couple extra steps, guys. And you get 75 over 900, and I'm going to round to the nearest tenth, so I get hundredth, I get 0.08, or 8%. So this is just a selection of the different problems you guys will see. Pretty straightforward, and we'll do our homework in class tomorrow, guys.